I'm Jerry Schubel, president of the Aquarium, and it's great to see so many of you here this evening. This is the kickoff for a process and a dialogue that's going to go on at least until next May. This is done in collaboration with the Nature Conservancy, the Art Center College of Design in Pasadena, with a virtual reality company that you will hear from this evening. And also, we're going to be joined later this fall and into the spring by a group of mid-career people seeking MBAs at Cal State Long Beach. And they need projects, and their project will be to look at what's at stake financially if we were to lose the Peninsula, Belmont shore, and Naples. And that can be very important. This is an unfunded project by the Aquarium. We're spending a lot of time and energy and money on it because we think it's very important to this city. These are important parts of our city. And when we get all done with this next summer, there will be few, if any, areas of Long Beach, coastal areas, that have had the same scrutiny of different options for dealing with sea level rise, short-term, mid-term, and long-term. So our goal, the Aquarium's goal, is to have a process that will develop a portfolio of strategies and tactics that will allow homeowners to stay in their homes as long as possible in the study area of the Peninsula, Naples, and Belmont shore, and to stay there comfortably, and if and when strategic relocation, sometimes referred to as strategic retreat, a phrase I hate, if strategic managed relocation becomes necessary or desirable, it can be done with the least emotional and economic impact on homeowners. To do this, over the next 8 months or so, we're going to be providing all of you with all of the facts, with some of the views of some of the best scientists from around this country, and even, as you see tonight, internationally. And Art Center will bring a different perspective. They're not scientists, they're designers. And they often bring different perspectives. Most of them won't be useful, but all you need is one good idea. The Rhode Island School of Design just recently did a study for Providence, and we're going to follow some of that. Some of the city's best beaches are in these most vulnerable areas, and we want to ensure that people throughout this city will have access to those beaches. This will become increasingly important as the climate gets warmer and people seek relief to get out of the city. And you have to remember that many people in this city do not have air conditioning, and the beach is a wonderful and important outlook. So this is the way this evening is going to go. We're going to hear briefly from Dr. Alyssa Mann. She's the Coastal Project Director of the Nature Conservancy. She will introduce Giulio Calillo, who's the expert on virtual reality, and he has flown the study area. Then I will introduce Dr. Gary Griggs, and I will provide an introduction to him. And then after that, after Gary's done, we will hear from two French scientists who are visiting the United States, and they're studying similar problems in France. And then I hope that we will have a chance for a Q&A at the end with all of you, but we will end the evening by 9:15. It's now my pleasure to introduce Alyssa Newton-Mann, who's the Coastal Project Director of the Nature Conservancy. Alyssa.
Oh. There we go. Not quite as tall. Good evening, everyone. And thank you, Jerry, and the Aquarium of the Pacific for hosting tonight's event, and for your leadership, Jerry, in creating a more resilient and thriving Long Beach. The Nature Conservancy is thrilled to partner with the Aquarium of the Pacific on this project to create opportunities for a community dialogue around sea level rise and pathways to a more resilient Long Beach, both in the near term and for future generations. Can you guys hear me okay? I feel like okay, great. My name is Alyssa Mann. I am the Project Director for Disaster Resilience for the California chapter of the Nature Conservancy. At the Nature Conservancy, we focus on developing lasting solutions that enhance resilience across our communities and landscapes. Part of what I work on in California is coastal resilience, how sea level rise fueled by climate change will significantly alter the California coastline as we know it, and what we are doing at the Nature Conservancy to address these challenges. How we really need to reshape California's future into one that protects people's lives and livelihoods while also preserving and restoring our irreplaceable natural landscapes. Our solutions offer a path to smart, sustainable development and adaptation, one that incorporates and benefits nature. At the Nature Conservancies, we spent a lot of time understanding the risks and potential impacts of sea level rise and coastal erosion, along with storms on our communities in California and really around the world. That includes our natural resources, our built environment, and people. We are also focused on understanding the role of nature in reducing these risks and potential impacts on our coast, really trying to understand and document the risk reduction benefits that nature can provide. We're also really interested in helping communities have productive conversations on the full range of solutions and the appropriate circumstances and time horizons when those might come into play. That includes nature-based solutions and multi-benefit solutions, as well as exploring adaptation pathways that may lead to or include managed retreat down the road. As Jerry mentioned, for this project over the next few months, we will be convening community dialogues or focus groups to hear and understand your concerns about the future of Long Beach and the Peninsula area, your perspectives on adaptation options, managed retreat, and different scenarios, as well as opportunities to hear, like tonight, to hear from scientists and experts around the issue and some of the innovative approaches being considered out there. We are thrilled to partner with the Art Center School of Design, as well as Virtual Planet, we are working with to develop a virtual reality experience to visualize the potential impacts and solutions in a very hyper-realistic and immersive way. I'm pleased to introduce Dr. Giuliano Khalil, who is both a co-founder of Virtual Planet Technologies, as well as a professor at the Middlebury Institute of International Studies in Monterey, where he teaches climate adaptation. Thank you.
Hello, everyone. Thank you so much, Alyssa. Thank you, Jerry, for an invitation. So could we get the slides going, please? Oh, sorry. Let's see. How's that? Is that good? Okay. So 1 second. And go. All right. So as Alyssa mentioned, we are working to develop a virtual reality experience that will showcase some of the impacts and projected risks here at the Peninsula, but as well as some of adaptation options. So it's a really nice area. But today, and I think a lot of you have seen graphs like this, the way we communicate risks and solutions is through a 2D map with some blue areas that are showing potential flooding. And it does its job, but there are better ways of communicating risk in a way that folks can relate to and really understand what's going on, and also visualize some of the solutions in a way that's more realistic and immersive. So why are we doing virtual reality? And that's the only slide I have with text, I promise. So VR there's some emerging research showing that VR can increase altruistic and positive health behavior, also preparation for natural disasters. So there was a study in 2013 from 2 Dutch scientists that showed that experiencing flooding in 3D, it wasn't even virtual reality, it was just on a computer screen where you could navigate and see kind of experience a flooding event. So folks that experienced that in the 3D environment showed higher intent to evacuate from flood-prone areas and also to purchase flood insurance. So we're tapping into that. And the interesting thing with virtual reality is that even though you know that you're not really there and that what you're seeing is not real, but to your body, there's no difference. You physiologically react the same way. So you get excited, your palms start to sweat, your heart beats faster. So it's really impressive how it really drives home some of these things. So the steps that we take to create this tool, the first thing, as Jerry alluded to, we fly drones over the area. I was out in the Peninsula a few months ago. Maybe some of you saw an annoying drone going by. And we're done with that. And the idea is that we take, for this project, we took about 2,500 photos from the whole peninsula, and then we create these 3D models that we use to do the visualization. So the second step that we do is that we bring those models into a virtual room. So you put the goggles on, and you can see the models on a table. And, oh, that jumped quite fast. All right, so we're moving right along. So you put the 3D models on a table, and then you can manipulate and slide that bar that you see. Let's see if I can figure this out. All right. So when you're in the experience, you can drag this to the right, and then you will see sea levels kind of rising in the model. And then there is an option to the right there what says adaptation. So once we design, we'll get the good ideas from the design, the art school, and then we're going to incorporate that into the tool as well, so we can see what the vision for the city is and some adaptation options and how they reduce some of those future risks. Another feature that we have on the tool is this really cool aerial view. So this is a 360 image from the peninsula, and you can also see parts of Belmont shores. You can see across the river, Seal Beach. You can see other parts of Long Beach and Naples. And over here as well, you have that option to slide. It's not quite, this is a work in progress, but I just want to give you a preview of what's coming and hopefully get you hooked in and so you can participate on the project. This is kind of an example of what it's going to look like. So as you slide the bar, you can see that this is a park on the East Coast that's getting flooded. And over here, one of the solutions they're looking at is using dredge materials to raise the bay a little bit, put some soil, and do a living shoreline solution to protect that park from sea level rise. And this is just a quick video we put together, just showing all the steps that I mentioned too. It's about 40 seconds. And you can see kind of the model. We start with a very thin point cloud, and then we intensify it, make it into a 3D model. We have a virtual blimp that you can fly and look at the area there. And then there's a virtual room that you can see, and we tailor that to the project. So we're thinking of doing something, maybe a room in the aquarium that you can look at. And then the 3D models kind of show on the table. Yeah, and I just want to give you like a taste. So thank you very much.
Thank you, Giuliano. So by the end of this, we want to bring to this study area all the tools and techniques and models and ideas possible so that we can evaluate all of the different options, as I said, short-term, medium-term, and longer-term. And I want to thank Ron Salk. He let Giuliano come into his house and charge the batteries of these drones a few weeks ago. Now I want to introduce my good friend and colleague, Dr. Gary Griggs. Gary Griggs is a distinguished professor of Earth and Planetary Sciences at UC Santa Cruz. He's been there for 51 years. For 26 of those years, he was the director of the Institute of Marine Sciences. The person you just heard from was his 72nd graduate student, right? And Gary's won just about every award one can get for teaching, for university service, for research. And in 2009, the California Coastal Commission and Sunset Magazine named him one of California's coastal heroes. He's been here a number of times to speak, and he's very involved in a similar study going on in Santa Cruz. That's mostly a cliffed area, and we want to work together alongside of them so we can have case studies for a cliffed area and an area with a low-lying shoreline. And he writes a a column for the local newspaper, and he's been doing it for 9 years, and he has just finished his 9th and 10th books, most of which deal with the California coast. He got his BA in geology from Santa Barbara and his PhD in oceanography from Oregon State University in Corvallis. Please join me in welcoming Dr. Gary Griggs.
So is this our advancer? Okay. I'll just ask you one thing when we begin. Don't shoot the messenger. So the shoreline is probably the most important line on the planet, which I think all of you appreciate. But it's moving. It's moving towards us. It's moving towards us because sea level is rising, and sea level is rising because the planet's warming, which does two things. As seawater warms, it expands, which raises sea level, and ice melts. And all ice melts at 32 degrees Fahrenheit. It doesn't matter if you're a Republican or a Democrat. So what I want to try to do tonight is just give you a little sort of background on climate and sea level, sort of what we've been observing, what we know and don't know about the future, with a connection to the Long Beach Peninsula. And I think this is out there somewhere, but I don't know exactly where. But it gives us some sense of what we're already experiencing now during extreme events. So we don't get to vote on climate change. That may probably sound obvious to most of you, but in fact it's occurring, and this is sort of a look at average or mean global temperatures going back. Somehow we magically started measuring things in about 1880, and if we look at the average between about 1900 and 1960, that comes out 0. So we're looking at anomalies or differences from there over time. And what we're seeing is globally things are getting warmer, progressively warmer every year. So 54 years ago, I was in graduate school at Oregon State University out in the North Pacific. It's not quite like Alameda's Bay. It's pretty rough. And what we were doing was actually collecting sediment cores from the deep sea floor, maybe 15,000 feet of water. And it's called piston coring. And what we do is actually drop a weighted core into the seafloor, bring back the sediment, open that up, and look at the history that tells us. So we were going back maybe 50, 60,000 years, not long in geologic time. But what became obvious in the work I was doing was when we looked at the surface sediments, the most recent warm period we're in now, the sediments were dominated by a particular kind of plankton called radiolaria that were indicative of warm conditions, warm water. And as we went back in time, we found it transitioned to a period that was characterized by these colder water planktonic foraminifera, also very common microfossils. And these are very, very small. And we could go back in time and see warm, cool, warm, cool. So I wasn't unique in doing that, but it kind of made me aware of the climate change we've been experiencing for tens of thousands of years. Now we've actually drilled into the deep sea floor. We've been doing that for over 50 years, and we've gone back about 65 million years. Those sediments record climate change around the world. We've drilled in all the world's ocean basins, and the records are very consistent. We have now been drilling in the ice of the Antarctic and also Greenland. We've gone back about 850,000 years. We've drilled down about a little over 2 miles. Those records of ice show climate changes. In the southeastern California, we have bristlecone pines that live close to 5,000 years, and many trees, including these, actually include climate in their growth rings. And we actually have deep water coral off California that are not reef-building coral, but they can live to be several thousand years, and their stalks are much like tree rings that record climate in the overlying water. So these are long-term records way before humans came on the scene and started influencing things for the most part. And a fundamental part of our climate change that we need to understand, we've been having climate change ever since we've had an Earth and a sun. One major factor that has affected that is the fact that the Earth and the sun don't have a constant relationship to one another, but there are 3 cycles that we've understood for some time. The Earth actually has a wobble on its axis that has a cycle of about 26,000 years. So as we get closer to the sun, it's warmer. As we get further away, it gets cooler. The Earth has a tilt on its axis, which gives us the seasons, but that tilt actually changes over a couple of degrees, so we lean closer to the sun or further away. Cycle of about 41,000 years. And the orbit around the sun is not a circle, but it's an ellipse. So we can get closer or further, again, affecting how much solar energy we get, and that has a cycle of about 100,000 years. And those are all operating at the same time, but not all in phase. So we now know, I should say we now believe pretty firmly, Earth's about 4.5 billion years old. And within about, well, a quick aside, when I was in a geology class as an undergraduate, the professor came in one day and said the Earth's about 4.5 billion years old. In another 4 to 5 million years, the sun's going to burn out and it's all going to be over. And professor looked out into the class, and there was some kid that obviously was quite upset. And he said, is there a problem? And the student said, did you say 4.5 billion or 4.5 million? And the professor says, 4.5 billion. And the student said, wow, that was close. So geologic time is long. But we think within about 100 million years of the Earth's formation, it was hit by a small planet, which has even been given a name, Theia, about the size of Mars. And it did a number of things, but it actually took some of the molten, heavier material that went into the core of the Earth. It sort of glanced off to some degree and took part of the surface of the Earth off, so the continents don't cover the entire Earth. That material in the core of that other planet became the moon. It was captured by the Earth's gravitational field. The other thing it did, it threw the Earth off of its vertical axis and its sort of symmetry. So it gave us a wobble and a tilt and this eccentric orbit, which drives climate along with a few other things. But we have greatly modified that. In the last roughly 150 years, we have changed the Earth's atmosphere. We've added a lot of carbon dioxide and methane and other things, in large part from burning fossil fuels and destroying vegetation. So that's begun to change this climate we've experienced for hundreds of millions of years. It's sort of like we keep rolling the window in the car up a little higher with this greenhouse effect. One of the places we've been able to extract that record, as I mentioned, is our ice cores from Antarctica that go back now a little over 800,000 years. And these are carbon dioxide contents taken from ice cores. So when snow falls, a little bit of air is trapped in that snow. So when it freezes to ice, we trap that ancient atmosphere. We can go in after we've drilled the ice, extract that, and analyze its chemistry. And what we're seeing is over the last 850,000 years, carbon dioxide is a very small percent of the atmosphere. Nitrogen is roughly 80%, oxygen is 20%. Tiny bit, parts per million is carbon dioxide, but it's a very powerful greenhouse gas. So carbon dioxide varied from about 185 parts per million to maybe 275 over the length of those cores. But now we're way up at 412. So it's way out of the range of anything we've experienced in the last 850,000 years. And this is lining up with the Industrial Revolution, basically. So back in the mid-50s, the then director of Scripps Institute of Oceanography, Roger Revelle, who was a brilliant man that realized, because we've known for some time that carbon dioxide was a greenhouse gas, sent a young Charles Keeling to Hawaii to set up an observatory on the top of Mauna Loa to measure carbon dioxide. Why did he go to Mauna Loa? Wasn't San Diego good enough? Well, we got a lot of cars and contamination, so he wanted a place that was pretty clean. Charles said, oh gosh, do I have to go to Hawaii? La Jolla was nice, so he went and spent the rest of his life there. He actually began to set the instruments up, and he was awarded the National Medal of Honor, and then in about 2008 he passed, and his son now, Ralph Keeling, took it over. But what you can see from this curve, and these are seasonal differences in carbon dioxide because of photosynthesis and so forth. So not only is it increasing, but the rate is increasing. It's not just a straight line, but it's an increasing line. That's because we're just burning more fossil fuels every year. And there's actually a little plot here that shows back in the early years, it was increasing by small parts per million, and virtually every year that's gone up, and now we're increasing still. So thank you all for driving your Priuses, but we got a big job ahead of us to cut back on carbon dioxide emissions. So if we go back in time, we can actually see global temperature, slightly different version of this, along with carbon dioxide, so those are sort of matching each other. But way back in the 1800s, a Swedish chemist, first sort of building on the work of a Scotchman, figured out that carbon dioxide was a greenhouse gas. It trapped heat. And we have natural greenhouse gases in the atmosphere. We have carbon dioxide, we have water vapor, we have methane. Those give us a global average temperature of about 60 degrees Fahrenheit. Without those natural greenhouse gases, the average temperature on the Earth would be about 0. So those are beneficial, but the problem is they're increasing. And along with temperature increase, which is following carbon dioxide, sea level is rising, as I mentioned in the beginning, because the warmer it gets, the more ice melts, the more seawater expands. So what we're seeing here is actually from tide gauges, water level recorders around the planet, which show a lot of scatter because these are on land, and they're reflecting what sea level is doing relative to the land. So if the land is rising or sinking, those are going to vary. But back in 1993, some really brilliant people actually figured out that we could measure this from space in an absolute way, launched some satellites, and we're actually measuring this down to 100th of a millimeter. I don't know how my cell phone works, and I don't know how this works, except they have to know exactly where those satellites are down to 100th of a millimeter all the time to get those measurements, because they're sending radar beams down to the ocean surface, millions of those all the time, and averaging those. So what's happening is the rate is increasing. As the Earth warms, ice melts, and so these are sea level rise, sea level patterns back to about 350,000 years ago. This is 0 today. And these are basically the ice ages. So roughly 100,000 year cycles, 125,000 year cycles, close to that solar cycle, the orbit of the Earth around the sun, and we can see some longer, I should say shorter 40-some thousand year cycles. But you can see these glacial periods when we get cold, we take lots of ocean water, put it on the land as glaciers. The last ice age, we took about 10 million cubic miles of water out of the ocean. Most of Canada, Alaska, lots of North America was covered with ice. Seattle was under 3,000 feet of ice. Cape Cod, the Great Lakes. It was a very different planet, but all that ice came out of the ocean. So this has happened repeatedly. The last ice age ended roughly 20,000 years ago, and each time that happened, we lowered sea level about 400 feet. That's what happened if we take 10 million cubic miles of water out of the ocean. So sea level went down 120 meters, 400 feet, then came back up to where it is today. But if you look at what we call 0 today, that's sort of artificial. If we'd been here any time in the past, sea level would have been someplace else. Does that make sense? Because it's been going up and down. We just happened to come on at a warm time. But any other time, this would have been 100 meters lower, 200 feet lower, whatever. This is that same curve, but only the last 24,000 years. So this is going from 24,000 years ago to today, and this is sea level relative to 400 feet. So it was down about 400 feet or so. It rose over 18,000 years, as the last ice age ended, ice melted, seawater expanded, at about a half an inch a year. 48 inches per century, considerably higher than we see today. That was the average. We could watch that. We could stand out there on the shoreline almost and see a half an inch a year. But within that, there were some periods when it rose at least twice that fast, maybe 8 feet per century. And we believe these are now times when major ice sheet collapse occurred in Antarctica and these glaciers surged into the ocean. That's what we're monitoring now in Antarctica, trying to figure out what's going to happen next. There's a lot of concern, but we're still a long way from knowing exactly when that's going to happen. About 8,000 years ago, sea level slowed, and for that period, it rose maybe a 20th of an inch a year, a millimeter. And that happens to correspond to the whole period of human civilization. So throughout human civilization, we have never had to deal with sea level rise before. So this is a new thing. We weren't prepared for that. Today, from satellites, we know the rate is about a 1/7 of an inch, a little over 13 inches per century. And in all likelihood, we now know that rate is accelerating. So sometime in the future, it's going to be considerably higher, which is partly why all this is happening. And I will say, sort of a bold statement, that may be the biggest challenge human civilization has ever had to face. I mean, we have disease outbreaks and other things. We figure out a vaccination, but this is global. It affects the whole Earth, and it happens very, very slowly, which is a good thing and a bad thing, but it takes a long time to turn it around. So if we look at the information from satellites, this is the record since we launched those in 1993. The average rate over this period, as I said, has been about 13 inches per 100 years. But if you look at the plot, in the very beginning, maybe the first 5 or 6 years, it was maybe 6 inches per 100 years. In this long middle stretch, which gives us the average, it was about 12.5 inches per 100 years. But if you look at the more recent values, they're considerably higher. So we're getting up close to 5 millimeters per year, almost 20 inches per 100 years. So that's the rate, and it's increasing. So that should concern us. So bring this a little closer to home. At the end of the last ice age, none of us were here. Jerry might have been here, I don't know. This is where the coastline was. So here's the area we're talking about tonight. So the coastline was roughly 6, 8, 10, 15 miles offshore. The water was 400 feet lower than it is today. So what's happened in the subsequent 18,000 years as the ice melted, some ice melted, and water expanded, we moved the shoreline here inward about 10 miles, or an average of about 3 feet per year. So this is just looking at where sea level was, where it is today, and the distance. And we can do this around the coasts of the planet. So one of the ways to think about what's possible in the future is how much ice is still out there. I could ask you questions like, these are all the mountain glaciers in the world. So we have Patagonia, the Alps, the Andes, the Himalayas. If we melted all that ice, how much might sea level rise? You know, that's not the answer you carry around in the elevator, but it might be a good one. About 2 feet. Not bad. I mean, 2 feet's a problem for a lot of places, but it's not going to take out the coastal regions of the world. Then we have Greenland. About 24 feet. We'd be in trouble here. I know I'm not going to tell you about the Long Beach Peninsula and Alamedas and Balboa and New York City and Miami and Guangzhou and Hong Kong and Shanghai, because they're all in deep trouble. And then we have Antarctica, which is the big, massive ice, about 190 feet. So if you add those all up, we have over 200 feet of potential sea level rise locked up in the ice. That's not going to melt tomorrow, this century, next century. We don't really know. It's melted in the geologic past. We had a period called hothouse Earth when it all melted. We had another period called snowball Earth when everything was covered with ice. So the Earth has gone through some big natural cycles. The difference is there were no people there to deal with it. So the question is, what if it all melted? I'm not trying to frighten you. This is just some scientific background. So somebody did a plot recently of that 216 feet. This would be Asia. So where you see this light blue line, that's the present coastline. And these are all the areas, large parts of China, parts of most of Bangladesh, and a lot of big cities. Europe. The Low Countries don't exist anymore with melting all that ice. And you can see the Caspian Sea gets much bigger. A lot of UK is underwater. So we can gloat about this for a little while, but then we come to the US. We have a very large inland sea in California. Florida's almost gone. Much of the East Coast, very different. Jerry mentioned a low-lying shoreline. Much of that would go underwater. And this is not going to happen anytime soon, but that's the potential that's there. Somebody else did an interesting, you can buy this map. I don't know why. There's some variations in what sea level could do if all the ice melt. In part, it's because the way we measure all the ice in Antarctica and Greenland uses radar and some other things. So some people said, well, it's more than 216. It might be 260. So this is more for humor than anything else because they have these interesting names like, you know, Isla Palos Verdes and Straight Outta Compton. And I think there's something like Irvine something Island. Anyway, so this is another extreme, but it's kind of important to keep that in perspective. So over millions of years, hundreds of millions of years, sea level's gone up and down 300 or 400 feet. And what's interesting is natural environments have responded without people being in the way. We still have coral reefs that live very close to sea level. We have mangroves in tropical environments that are still there and healthy. We have seagrass and other environments. So the natural environments, which we spend a lot of time worrying about and trying to sort of preserve and protect, historically have done okay. Cities, not so much. Cities have never had to deal with sea level rise before. So this is a new thing. And if we look around the world today, there's something like 150 million people, plus or minus a few, living within 1 meter, 3 feet of high tide. And in the US, something like 13 million people living within 6 feet of high tide. Most of them are in Florida and along the East Coast, which is much lower. So there's two different kinds of concerns. One are short-term, things like getting very high tides and large waves, king tides at the same time, or El Nino events. When we elevate sea level, we often have storms from different directions. And then there's long-term hazards, sea level rise, which produces two things. One is short-term flooding in low-lying areas, which will become permanent inundation, and then more frequent wave attack of sea cliffs, so erosion of cliffs and bluffs. So this is off into the future, but what we're beginning to be concerned about. But these are things we're experiencing now. So we do have these already. I mean, you've already seen these. This is Belmont Shores at king tide a couple of years ago. Lots of photos on the king tides website, these very high astronomical tides we see a couple times a year. And the big El Nino of 1983, one of the worst we've experienced in a century. These are showing 3 of the Noaa tide gauges, San Diego, Los Angeles, San Francisco, Seattle. And these are what predicted high tide would be if you looked at your tide tables. These are what actually occurred, and these are the differences. So around LA, this was the highest water level in 59 years that has ever been recorded. San Francisco was 1.5 feet above expected, and Seattle was 2.5 feet. So these are important to keep in mind relative to sea level rise. We've already had 1 foot of sea level rise that stayed around for a couple of months. So that's nothing new. It's just that we're going to be on this ramp with an increasing slope where this becomes more permanent. A little bit of perspective on sort of what the coastline here looked like historically. I'm not saying let's go back to the early Native Americans. But the coastline was very different, and there was islands out here, and if you've ever read 2 Years Before the Mast, or is it 3 years before the Mast? The accounts of landing here back in the early 1800s and trekking to sort of the missions and so forth is fascinating to see what it looked like way back then. But there was this sort of interesting shape of the original shoreline. It's what we call a log spiral, and we see a lot of these in California. Point Reyes, Coronado in San Diego, the Silver Strand, and Half Moon Bay. And this is sort of what happens when waves hit a hard barrier and then bend or refract around. They start to create this perfect hook-shaped bay that's actually the way a shell would uncoil. It's like an abalone shell, and we see these all along the California coast. So that's sort of an equilibrium balanced coast. And that's what we had here initially. This very smooth, because the wave energy refracted around the point here and then spread it out. So we created sort of a balanced coastline. And you can see the early map sort of depicted that. A lot has happened since the 1700s. You can still, with a little imagination, sort of see what that curve looked like, but with LA Long Beach Harbor, the breakwater, we've done something, we've made major changes in investing in ports and harbors and the economy and exports and imports. And just to give you some sense, this is Half Moon Bay, south of San Francisco. And these are the way the wave patterns come in and bend or refract as they enter shallow water. And this coastline was in equilibrium or balanced up until about 1959. And then they built a breakwater to provide a harbor. And what happened was all the wave energy that was dissipated inside that bay now came down this breakwater and hit the coast right there. So this is what that area looks like today. It went from a few inches per year to 5-6 feet per year of erosion. There was a sewer line that's gone and a road that was gone, and now we put rocks in there. So this is one of the kinds of changes sort of in the way of progress that has pronounced down coast changes. And if we look at LA Long Beach Day, this is sort of a quick summary. We did the breakwater system for the harbors back in 1899. That sort of disrupted this equilibrium. The original estuaries and islands were sort of eliminated or greatly altered. We created Naples out of sort of the estuary of the San Gabriel River. We dredged canals and put that mud to create the island. Severe flooding caused the removal of the San Gabriel River further south. We built jetties. And interestingly, those rivers are still some of the major sand sources, as limited as they are. So we've really altered this coast so it doesn't behave the way it did decades ago, and that's not uncommon. Pictures you may have seen or know about Alamedas Bay and the kind of what Naples looked like before it was Naples in 1920. This is the early 20s. They're starting to sort of create Naples. And then in 1925, we could see it now as taking form. So it started out as a marsh or an estuary, and it's been built up and built over. So that actually took the ground up. Extracting oil, beginning in Signal Hill in the 20s, led to subsidence. This is sort of an amazing picture to me because of our Coastal Commission environmental impact analysis today. I wonder if they did an EAR or got a permit for these. But they're just kind of loving the coast, and they were just sucking that oil out of Wilmington. But pumping out water, pumping out oil creates some voids in the subsurface, and what typically happens is the ground begins to subside until we figure out how to get that under control. So sort of the center of Long Beach Harbor today, it went down 28 feet, subsided 28 feet. You can see coming down to the peninsula here was on the order of a foot or two. Then what happened after the consequences of that were understood, they began to pump salt water back in under pressure, which not only begin to arrest the subsidence, but it also leads to secondary recovery because the oil is lighter than water. They get more oil out than if they didn't do anything. So as far as I know, this has pretty much been arrested or halted, but it did lead to some local subsidence. Takes a little while to figure that one out, but. So one of the things we need to keep in mind is short-term versus long-term. And we do have a tide gauge, an official NOAA tide gauge in LA that's now almost a century old. So these were put in originally for navigation, not for sea level rise. We weren't talking about sea level rise back in the 20s. So what you can see is the record of what water has been doing relative to the land in Los Angeles. And a couple of things, if you look at the rate, it's about 1 millimeter per year versus the global numbers of 2 or over 3. So sea level is rising here maybe a third of the global rate. That's a good thing. So why is that happening? Is the ocean different here? Well, it's got to be because the land is rising. So if this is global sea level and this is Los Angeles, we're actually gaining a little bit. It's still rising, but not nearly as fast. And there's other places we can go. Alaska, for example, where Alaska was covered with ice during the Ice Age, it was depressed. As the Ice Age ended, the ice was removed, Alaska began to rebound. Sort of like sitting on your mattress. Get up, mattress rises quickly. Only the land rises much more slowly. It takes tens of thousands of years. So in Alaska, sea level is actually dropping relative to the land because even though global sea level is rising, the land is rising much faster. The opposite of that is New Orleans. Don't buy property in New Orleans. New Orleans is sinking. Partly it's the huge load of sediments from the Mississippi Delta, partly it's groundwater, partly it's oil. So here's global sea level. The same is in Alaska, but New Orleans is sinking. So their sea level rise is 3 or 4 times the global average. They're in deep yogurt or something. So the local tide gauge here shows that its sea level is instead of 13 inches per century, it's 4 inches. Not bad. That's going to slow things down. But the other thing you can see here, this is 1983. This is the 1983 El Nino, where this warm bulge of water raised sea level for here maybe 15 centimeters is a half a foot, 4 months. The 1997-98 El Nino, more than that, the 2015-16 El Nino. In fact, we had some big ones back in the 40s and so forth. So these are the short-term events that are going to be more important probably until at least 2050 that we need to think about while we're also counting how many millimeters per year sea level is rising. 2 documents that came out over the last 2 years. One was done by the Ocean Sciences Trust that Jerry is on. Well, we're both on it. And this was ordered by Governor Brown. He said, I want to know what's happening in California. It was in part due to new work in the Antarctic that was showing how fast ice might be melting, what could happen with these ice sheet collapses and glaciers coming into the ocean. So this projected future sea levels in a number of different ways. And then the Ocean Protection Council, another state agency, actually took that science and put it out in another document called Sea Level Rise Guidance, which was more applicable to cities and counties. These are online, so you can get these. There's no big secrets. And then Long Beach did their own study and used those same numbers to bring it sort of home. And it's always hard to show a bunch of numbers on a plot, so I kept this to a minimum. But these are the kinds of numbers in much more detail. This is for the Los Angeles tide gauge. What we could expect in the future. And so some of the uncertainties are, a big one is, what are the carbon dioxide emissions going to be in the future? So we actually have numbers here for different years into the future, 2030, which is just 11 years away, 2050, 2100. In the near future, greenhouse gas emissions don't have a huge effect. but they're going to have an increasing effect. So this is 2100, which none of us are worrying about. This is low emissions, meaning we get control on carbon emissions, cut back, reduce, eliminate fossil fuels, go for sustainable energy sources, and then high emissions. And you can start to see there's some differences over here that are significant. And then, because we don't have a single answer, I think everybody wants to know, where's sea level going to be, how high, by what time? Well, we don't know how much more carbon dioxide is going to be released. There's some model uncertainties because we don't understand exactly what's happening in Antarctica and Greenland. So this is sort of like trying to think of an analogy that's not going to be depressing. I'll take one that affects everybody. Life insurance. Well, you could say on average we're going to live to be 78. But so this is the median. This is sort of the midpoint of all those estimates. 4 inches more by 2030, 8 inches by 2050, depending on emissions, 16 inches or 26 inches, way off, 80 years into the future. But if we want to expand that a little bit and say, okay, there's a 2/3 probability, instead of the midpoint, that it falls in this range, and we start to see a little more spread. And then we can go to a 1 in 20 chance. It's a 5% probability. It's going to be a little bit higher off into the future. And we're starting to get up to numbers that are 4 feet. And then there's a 1 in 200 chance. So these are all probabilities that are kind of hard to deal with, but it's because we don't know for sure. And what is in those documents is saying, well, do you want to be a low-risk aversion or high-risk? So if you don't want to take any chances, you don't want to build a new sewage treatment plant using the midpoint. You want to be way out over here if you're going to invest $1 billion or a large amount of money. What if we're going to build a new San Francisco airport? We better make sure we're covering our bases for the next 50 to 100 years. If we're building a bike path or a parking lot, we can be a little looser. So these are some of the ranges why it makes it difficult when you ask me, what's it going to be in my front porch? Well, somewhere in there. I'll just skip through these really quickly. So there are a number of sites where you can actually go online, and Giuliano showed just a glimpse of this. So this is a Noaa sea level rise viewer, which is based simply on elevation. What's the land elevation? The most accurate numbers we have for land elevation. So this is today where the water would be, and mean high or high water, so the average of the high tides. If it's blue, it's water. If it's green, means it's below mean high or high water, but it's separated by some barrier. It could be a road or a levee or a dike or something. So it's below sea level, but it's not wet. So now we can slide, and you can do this on your computer at home tonight. I'm sure that's all you're going to want to go back and do. We can slide this up in 1 foot increments. And it's a little hard to see what just happened, but you can start to see a few areas that are blue, a few more that are green, and some light blue here. So 1 foot could be by 2030. We can go to 2 feet. Then things start to get a little messy. Again, this is why I said don't shoot the messenger. This is Noaa, our federal agency, and it's, again, based on elevation and just adding water to it. And Giuliano said flying over it, you get a different view. So anything that's light blue is now wet. If it's green, it's below that level, but it's still isolated by some barrier. How much higher you want to go? 3 feet. I mean, 3 feet is possible by 2100. It could be before that, and we don't know. I already had 2 other ones in here, so I'm going to do that. So just close your eyes, okay? So this is 5 feet. And there's a lot of other places that look like this. And then just for the heck of it, we did 10 feet. I didn't do 10 feet. Noaa did 10 feet. So these are kind of scary, but I think we need to go back and say, okay, what's likely during my lifetime, the near future? I don't need to say anything about that. In the sense that this is from Scientific American. I'm not quite sure where this was reported. But if you take 10 feet of sea level rise around the U.S., around California, we pretty much wipe out most coastal cities. So 10 feet is an extreme. In our study in California, the people that run these models said 10 feet is possible, very low probability by 2100, but we have no idea what the probability is. We don't understand the ice that well. So that's an extreme, but that's 81 years off into the future. But when you see things like this, you say, yeah, we can't deal with that. And this isn't tomorrow. It's perhaps way off in the future. I've been looking for this sign. I've never found it, but I think it's a useful sort of a metaphor. So what are the options we have for responding to sea level rise and climate in the future and extreme events? So beach nourishment, armor, accommodations, sand retention, groins. We could call this relocation, managed retreat, unmanaged retreat, stepping back gracefully. I gave a talk recently to a similar group in Santa Cruz County. They were coastal homeowners, and they wanted to know what was happening on the coast and what we knew about the science and so forth. And the president of the homeowners group said to me, there's only 2 words you cannot mention. The dreaded managed retreat. So I tried to avoid that, so I put this slide up, and I put this in very, very faint letters so that you could see it if you squinted. But I understand this is not something anybody wants to think about or talk about, and I think it's important to think about way off in the future. I mean, there may be houses that are flooded today at high tides, and there's some that aren't going to be flooded for 100 years. So I think we need to get away from the idea of this is not evacuation and condemnation. It's beginning to look into the future and see what could happen and set some trigger points maybe, where if we get to this level, if your house is flooded now once a month, say, okay, I think we're at a point where we need to do something. Have we thought about what we're going to do? If you're on a sea cliff and you're within 10 feet of the edge, when you get to within 3 feet of the edge, we need to be prepared to do something. So that's, I think, a different way to think about it than somebody's coming to get you, they're going to take your house, and so forth. So beach nourishment has mostly been an East Coast phenomena, a little bit in this area. San Diego did 2 of these nourishments back in 2001, 2012. They spent $46 million, put 3.5 million cubic yards on the beach. And if you look at the surveys carefully, you'll find most of it was gone in 1 to 2 years. This is not a permanent solution. And what I would say is if the sand isn't staying there naturally, why should it stay because it came out of a dredge or a dump truck? It's not going to, unless we retain it somehow. So there's another big plan to spend another $150 million down there of our money, and I would say that's a very expensive, very short term. Armor is a very delicate topic. If we looked at California today for the entire coast, roughly 14% has been armored. But if you look the Big Sur coast, Northern California, not much has been armored, so the average comes down. But if you look at Southern California, 38% of the coast of San Diego, Orange, Los Angeles, Ventura counties have now been armored with some sort of structure. And these are some examples of those. The big change is taking place that I don't know how well publicized it is the original Coastal Act wasn't written with sea level rise and armoring necessarily in mind. So the language had some vagueness to it. And one of the parts of the original Coastal Act said, if an existing structure is threatened, you can apply for a coastal development permit for armor. The tricky language was existing. So this was written in 1976. Attorneys have been arguing ever since. Well, I built my house 2 years ago. It's existing. I want a seawall. People that wrote it in 1976, maybe had something else in mind. And for the subsequent 50 years, if your house was on the edge and threatened, you could come in and go through the process and go through the fees and go through the studies and still, in some cases, get a permit for a seawall or a vetment, some protection. Well, in the last year, the commission said, no, we're going back to the original Coastal Act. And if it was built after January 1, 1977, you are not eligible for a coastal protection permit. That's a huge change for California. And I don't think that's filtered down to probably everybody that lives on the coast. So that's going to change the 38%, and it's probably not going to go up a whole lot more. I do not think we're going to see a whole lot more seawalls or revetments, even though that is another, short-term to intermediate-term solution. Accommodation. This is Sausalito. I don't think we're all going to live in houseboats. There's just too many of us and they're too expensive. These are probably $1 million. Well, that may not be expensive anymore. Here's another kind of accommodation. I think the idea is you let the water go by you and then you come back and rebuild your house. But I don't think that's really a good example of accommodation. And then something that we've started working on recently, writing about, is most of our beaches in California occur because of the orientation of the coastline, where the sand stays, which way the waves are coming from, and whether there are barriers to sand transport. So some of those are natural, some are engineered, and if we look at Point Dume and Zuma Beach and Broad Beach, which gets a lot of publicity because of the people who live there, without this point, this beach wouldn't be here. So it's a natural groin, it's a natural headland. Here's another one down in, I think, Laguna. So this point sticks out and we have a nice wide beach. This is an artificial groin in Capitola where we built a groin, the beach accumulates and they have a nice summer beach. Without that, the beach would be much narrower. And we have these in Newport that have been there for decades and have been effective. We have them in Ventura. We have them in Santa Monica. But in recent years, this has been sort of they've been, I would think, generally discouraged. But what we're trying to do is say, with all the sand that flows through the California beaches and into submarine canyons where it's lost, there could be some benefits if these were done carefully in particular places, rather than losing all that sand forever to the deep sea. And then there's planned relocation. Not too many examples. Cape Hatteras Lighthouse, a big house on the outer bank of North Carolina. I mean, this cost $12 million, but it was a national park and it was sort of a monument. So we can move all kinds of things up to a point. I'm going to use one example for our colleagues from France. This is an example on the coast of France where this incredible storm hit. I think 47 people died. And apparently they were built in an area below sea level behind a sand berm. Some questions about whether they ever should have been built there. This storm hit, people died. I understand it was the central government that said, you're out of here. So this next shot, if you look at these houses and these houses and these houses, they're all gone. They decided the risk was too high. These houses have remained. I think there's a road here that acts as a barrier. So this is one example in another country of one extreme storm. There's another really interesting place, and I discovered a book a couple of years ago called Lost Towns of the Yorkshire Coast. So this is on the sort of east coast of England, UK, and they have lost 29 towns over 2,000 years. Since the time of the Romans, they've kept track of the shoreline and these towns. And these are where these towns were. It's been going back at 6 feet per year for 2,000 years. And this guy documented all that with this book. And I was writing this book on coasts, and I said, I really want to go there to see what it looks like today. So interestingly now, the land isn't Long Beach Peninsula or Balboa or Malibu. It's pastures and hayfields. So what they've done is they've built what they call caravan parks. So they're like mobile home parks, trailer parks, and people can rent a concrete pad with electricity and water and sewer. And this is where they spend their summer vacation, pretty inexpensively. But the coast is going back at 6 feet per year. So when you can see these roads that sort of go out and stop, when you get close to the edge, you bring in a truck and you hook up your mobile home and you go back to the back of the line and somebody else gets oceanfront property for 5 years. And as we well, as we drove across, we came into these signs, do not proceed, these roads go off into space, and this one has an interesting title of Clifftop Caravan Park. And these people are kind of happy out there, but some of them have moved, some are there at the front. So I think it's an example of, not California, but I would say this is what I would call resilient. They have responded by being flexible, but this is not the way California has been developed. So I'm not recommending that we move towards mobile homes on the peninsula. So I'm going to leave you sort of two other examples that you probably read about. One is Del Mar, and now most communities are having to update their local coastal programs. Del Mar has decided we're not going to include managed retreat. We're not moving back. And I think it's coming to the Coastal Commission in a couple of weeks, and it'll be interesting to see what happens. I think the staff is already recommending that plan does not get approved. So this is going to be sort of a bit of a battleground to see what's going to happen here. There's something similar happening in Pacifica where they had a mayor who was encouraging people to sort of think about this, and they recalled him and got rid of him. So there's a lot involved. And at the other end of the spectrum, Jakarta, which is like 10 million people, the leader of Indonesia said, we're going to move it. It's sinking at 5 or 6 feet per year. They can no longer afford to maintain the capital city of Indonesia. So Del Mar says, no, we can't do it. Jakarta says, we're going to move. Kind of amazing contrast, but part of my goal tonight was at least give you a sense of sort of the science behind what we know and what we don't know, and try to at least give you some sense that this is not something that's going to happen tomorrow, but the more we know about it, the more the people who live there get involved in how they feel about it, what they think, I think the better off we will be 10 years, 20 years, 30 years into the future. Thank you very much.
Thank you, Gary. So we're going to have questions at the end of all of our speakers. But I think Gary is right that sea level rise is probably the biggest challenge faced by modern humans. Our history of Homo sapiens goes back 200,000 years. So they've seen a lot of fluctuations in sea level over 200,000 years. But most of the development, as Gary pointed out, has happened during a period of stable sea level. It's interesting that most of the estimates of the upper bound of sea level at 2100, they were at 1 meter. In the report that came out last week by the IPCC, they raised it to 2 meters, being very probable by 2100. But it all depends on what we do. So we have to mitigate. Mitigate means reducing the driving forces of climate change. That is, eliminating, drastically, rapidly reducing greenhouse gas emissions, looking at agriculture as a source of greenhouse gases and land use practices. All of those are important. But if we went to zero tomorrow, there's a large enough inventory of CO2 in the atmosphere that the Earth would warm and sea level would continue to rise at least through the end of this century and probably much longer than that. So we also, I think then, if we're serious about this, we have to both dramatically reduce greenhouse gas emissions. We also have to fund the research to remove CO2 already in the atmosphere and lock it away. We know how to do it in the laboratory. We don't know how to scale it up, but it seems to me that's one of the things we have to do. And also we certainly have to learn how to adapt. And so I hope that by the end of this process, next May, that we will have looked at all of these options, short, medium, and long term, and we will have a good picture of what's possible and what will really make sense for Long Beach. Now, we're fortunate this evening to be joined by 2 scientists from France. They're experts on coastal processes, sea level rise, and managed relocation. They come to us as a result from USC Sea Grant, and we thank Phyllis Griffman. Phyllis is the Associate Director of the US Sea Grant Program, and she introduced us to these 2 scientists. The first is Dr. Sylvain Barone. He's a researcher in public policy in the National Research Institute of Science and Technology for the Environment and Agriculture at the University of Montpellier. Now, Montpellier is one of the largest, one of the oldest universities in the world. It was started in 1289. That's hard for us to get our arms around. When did Santa Cruz start? 1965. I think, you see Ermine started about the same time? 1289. So they've seen more of sea level fluctuations than we have. And Dr. Barone is going to be followed by Dr. Laura Michel. She's a professor at the same university, and they will be making this presentation together. And after it's over, we will get all of our speakers up on stage, and you can fire away with your questions. So please join me in welcoming our two French colleagues.
Okay. Good evening, and first of all, I would like to thank Jerry for his invitation. We are very happy to be here tonight. So we will present you a work in progress. We are working on sea level rise in France and in coastal management in France. So we have a map to present our study, which take part on the Mediterranean Sea. Here, at the top, it's a region which is called Occitania. And on the picture there, you can see the Gulf of Lion. It's the name of the part of Mediterranean Sea at this place. So in this coast, we have this kind of landscapes with the sea, and then a very low-lying area, a sandy beach, we call Lido, and then lagoons and ponds, and then inland. So it's a very flat coast with very few high points. You can see one of them just here, but there are very few. And it's also a coast with many towns on the beach. Yes. Okay. So, what are the vulnerabilities on this coast? First of one is a problem of erosion. We have a coastline retreat in most parts of the coast, in 22% of the coast of the Gulf of Lion. But of course, with many uncertainties to the extent to the retreat, and also it's not the same retreat in every part. Sorry. Ouais, mais j'ai plus fort.
You just have to get up and down, Jerry.
Ben ouais, mais je ne peux pas revenir là. Vas-y, c'était peut-être plus doué que moi. Oh, the pointer, but to the next. Okay. Okay. So here you can see a map of Europe with this. Sorry? Oh, sorry. You can see the map of Europe, and you can see we are in the red area here. This is a zoom on the Gulf of Lion, and you see many parts are with erosion here in red or orange. Okay. We have sea level rise hypothesis also with climate change plus or minus 1 meter in 2100. A big problem of loss of sediments due to dams to the main rivers and multiplication of sea storms since the 80s. Here you have a picture of a big storm in 1982, and here it was last year in March. And of course, we have also concomitants of events of floods and submersion. On this part, it's a very narrow strip line, and we have a very high concentration of people and activities. We have very strong demographic growth. It's one of the regions of France with the most important growth, demographic growth. We have also mass tourism with many ski resorts. In the 60s in France, we have a big state program to build new resort town on the Lido. Here it was before this program, and here the same place 20 years after. So with many resorts to develop tourism in the region. We have also many infrastructures on these very narrow strip lines, such as roads, railways, midi-channel, many highways also, many risks, floods, fire, and also we have many zoning for land use, for environmental and risks. Also, it's it's a region with an important social precariousness, with high level of unemployment, of precarious people, and also of precarious housing. As you can see here, often people have built sometimes mobile homes, sometimes hand cabins, and so on land that doesn't belong to that are private lands, but these houses are illegal. So we have, to sum up, we have huge economic and social stakes concentrated on this part of the coast. So we are, our question of research, we are political scientists, so we have a focus on the governance perspective, and because the political dimension is often underestimated in the analysis on political adaptation. And we are interested to how different actors are collaborating or faces difficulties to cooperate to manage the risk. And eventually the question is for us, who governs these coastal risks? So in France, we have national policies that have evolved during the time. In the 70s, the intervention of the French states, when we speak about state in France, it's a national state, the French state, In the 70s, the problem was of urbanization. We didn't speak about risk at this moment, and we had laws and to preserve natural areas from urbanization and to fight against the privatizations of the beach. So here with the Conservatory of the Coast, we have something equivalent here in California, and a law on the coastal law of 1986. Then the coastal risks emerged as public policy problem in the 80s, and especially in the 90s. And especially in 1995, a law created a national fund to prevent every natural risk. So it's a specificity in France, because this fund, which is a national fund, is funded with insurance premiums, which are taken on every citizen. When you pay your insurance, your home insurance in France, a part goes to this national fund. So there is a national solidarity in case of natural disaster, fire, flood, and so on. But it doesn't work for erosion, only for submersion. Then the big storm Xynthia in 2010 with 47 deaths, as it was said before, in France, that gave an acceleration in these policies, with two main national strategy at the national level, which are for two different risks. This one is for the risk of submersion and sea level. And it's related to this fund, so in case of natural disaster. And another one here, the National Shoreline Integrated Management Strategy, which is for the erosion. But in this case, the national states make mandatory local plans to forbid the building in areas. Sylvain will show you in a moment. And in this case, the state is promoting a strategic retreat. So the national states incite local authorities to organize the relocation of houses and infrastructures.
So in France, just like in most part of the world, I guess, we have a succession of two main periods. From the 60s, to the 80s, the objective was to fight against the sea. Oh, sorry. Yeah. So the multiplication of techniques like that, rocky spikes, breakwaters, static protections, riprap, etc., with many consequences, as you know, rise in public expenses. It's very expensive. Coastline artificialization and erosion transfers from one place to another. From the 2000s, we started talking about sustainable and integrated coastline management, with a mix of policy instruments and techniques, just like in California, I guess, with, first of all, land use regulation, regulatory zoning. This is an example of a regulatory map we have in France. So in the red zone, you can't build any new house. It's forbidden. I have another map, yes. In the what is not in red means that you have prescriptions on new buildings. And the yellow area is that you have to take into account the climate change projection in 2100. So it's kind of an anticipation of climate change. A second instrument, very important, is regional and urban planning. We also have, just like here, beach nourishment, living shorelines, dune restorations, etc. I'll show you an example of operation just in a few minutes. And we have, just like you, I guess, big questions and controversies around managed retreat. And we don't talk about managed retreat anymore. The word is kind of taboo. We say now spatial territorial recomposition. And of course, we still have riprap and dikes and so on. So just a slide on managed retreat, which is very important in the political debate. In France, maybe it's a difference with California. I'm interested in your point of view. It is a priority of the state. The national state is talking a lot about managed retreat, and all the strategies are talking about managed retreat or spatial recomposition, sorry. But the state is facing a lot of difficulties, which are financial. We don't have a fund to buy houses, even if they are less expensive than in California. It's a lot of administration, heavy procedures. It's very complicated. Managed retreat raises the question of where are you retreating, and we lack available land in coastal zones. And there is a big political issue because elected officials are looking, among other things, for blame avoidance. So there are very few expropriations of dwellings in our coast, but some relocation of infrastructures, such like roads, for example. And we have reflections in progress in France. There are law proposals talking about that, to share the cost of managed retreat, so that the cost is not only on the owner or only on the local government. One of the ideas is to create areas of temporary occupation where new types of leases can be developed. So the local authority or the state buys a house, and then the owner give a rent every month, and so there is a kind of sharing of the loss. But for the moment, it's only ideas, and there is no real legislative concretization. This is an example of a well-known operation on our coast. So it is very multi-instruments. It's a good example of policy mix. This is, for those who've been in France and who knows the southern coast, it's between Sète and Agde. We have everything we can have in terms of adaptation, coastal risk adaptation. We have beach nourishment, we have beach drains, swell attenuators, it is geotextile devices, submerged breakwaters, dune restoration with chestnut wood picket to capture the sand, dune restoration, and road retreat. Yeah. The road was really close to the beach and has been delocated. It is a 50 million euros operation. It's a partnership between the state and the regional council. and it is considered as a success in France. So what governance? I won't mention all the actors. There are many of them, but maybe it's a common point with California. The governance is fragmented and multi-level. The deep core, the hardcore factors are these ones. The French national state is playing a strong role in France. So it's the national state in Paris and with its regional and local bodies. The state elaborates strategies, guidelines, in line with the broader European Union directives. And there are regional declinations of these guidelines and these directives. The national state ensured the application of the coastal law, the 1986 coastal law, which prevents constructions, in partnership with the French Coastal Conservancy. Then there is the Regional Council, which plays a great role in planning, programming, and co-funding. The Regional Council is beyond the county level. Then municipalities and intercommunalities are playing a role in terms of local planning, contracting, and we have many stakeholders and private actors, the insurance sectors, scientists, the tourism sector, etc. This is our last slide. This is we are taking risk today. This is the comparison we started to elaborate between France and California. And we are very interested in your reactions and comments on this table. Yeah, the hazard, I won't present the hazards. Laura did it a few minutes ago, but the hazards are not really the same in France and in California. We don't talk really about sea level rise in France. It's not a word we use a lot. We rather talk about erosion, storms, floodings. In terms of stakes, the concentration of wells in California can't be compared, I guess. But the stakes are the same in France, but less contrasted in terms of difference between the wealthy people and the poorest people. We have some similar types of organizations. The state, it's the national state in France, it's the Californian state here. We have in France a coastal conservancy. We have local governments, NGOs, stakeholders, insurances. What we have not is an equivalent of CCC. There is not in France. And maybe what you don't have in California is the regional council, which is an elected authority, local governments, but at a higher level than the county. The main differences we think is differences in governance processes, which seems to be more ad hoc, bottom-up, with task forces in California, and more state-steered and top-down by the state in France. The instruments are quite the same. Maybe beach nourishment is more important here, especially in all the documents, local documents that are produced. What strikes us a lot is the attempt to make science and models available to the public. In France, it's more the state that produces regulatory documents and the legitimate science, and the public don't have good access to these models and science. Maybe it's one more difference. And incentive instruments are more developed in California. France is more based on regulation and regulatory maps. And we think California and the United States are more engaged on emergency, maybe because of hurricanes we don't have in France. The techniques are, again, quite the same. Seawalls, beach nourishment, here, actions on wetland. Maybe it's more like the same in France, but for maybe 10 years, public policy is more oriented towards green infrastructures and ecological engineering. And we have this big discourse around managed retreat, but with few actions for the moment. And for the funding, in California, local government, states, FEMA, and private donors, maybe some other actors. And in France, the state, local governments, the European Union, and these national funds, the Barnier funds, based on insurance premium and to back national solidarity. So this is some insights on the French case, and again, we are really interested in your comments on this table. Thank you very much.
If we could bring the house lights up and have all of our speakers come up front, and let's see. Maybe Juliana, you come on up front. We'll put you on one of these little stools. You're the youngest. Unless there's room to sit. All right, you can direct the question to the entire group, or you can direct the question to any one of our speakers. And I would like us to keep tonight for questions. There'll be plenty of opportunities for you to make statements, because as you heard from Melissa, we're going to have a number of listening groups and forums throughout the area of concern. So who has the first question? Raise your hand, we'll get a microphone. Right back there. All right, there's a microphone right there with you.
Yes, I heard the gentleman mentioned a 1986 law that prevented construction. What can you clarify that? I mean, we continue to build and build and build. So I'm very interested in how you got that passed.
Gary, I think that was you in the Coastal Act and construction.
Oh, it was in France.
Oh, it was in France. Oh, I'm sorry. Okay.
Is it working? Yeah. The 1986 coastal law aims at forbids construction within 100 meters strip, so you can't build any new buildings in this area. In non-urbanized areas, and in urban areas, you can just maintain your building, but you can't build any new houses, and that's the main objective of the coastal law.
But if you had a building already there, you could maintain it. Is that
Yes.
correct? Yes. All right, who has the next one? If you raise your hand right over here.
Is it possible to release some kind of material into the air to counteract the effect of carbon dioxide? Like if there were a giant volcano?
Yes. Who would like it? Gary, you're a tell us about Krakatoa.
Big on giant volcanoes. We call that geoengineering, and there's been a number of studies. The most recent one by the National Academy of Sciences brought a lot of really good people together, and basically they concluded at this point we don't know enough to start some project that we can't control. So we've talked about putting little mirrors up there to reflect sunlight back. And I think the problem is, even though Jerry mentioned the idea of sequestering carbon dioxide, atmosphere is really big. There's a lot of stuff up there. And anything we do on any sort of human scale is so small compared to the size of the atmosphere. I mean, people say, well, can't you just suck it out of there? Well, depending on what you call the atmosphere, is it the first 6 miles or 10 miles? And look at the size of the Earth. It's immense. Sort of like trying to lower the, or raise the pH of the ocean. How do you affect 330 million cubic miles of water that we've been adding stuff into? So I would say that's not off the table. But I think it's always tricky to try to solve one engineering problem with another engineering problem rather than going back to the basics and saying, okay, how do we just reduce? It's another comparable example is trying to take the plastic out of the ocean. Anybody that's looked at that carefully say, the amount is so big, the particles are so small, they're so deep, we got to just stop plastic at the source. So I don't think we're ready to try that, and I'm not sure that will ever be an overall solution.
On the geoengineering, I would disagree with you, Gary.
Sorry, I got to see it first.
There are two categories. There's what's called SRM, solar radiation management. That's what when a volcano erupts. So that's where you inject very small particles into the upper atmosphere. We know that you can cool the Earth if you do that. Krakatoa cooled it for several years. Now, does it have unintended consequences? That we're not sure. The other one, though, is called what's SRM. CDR, carbon dioxide removal. And there's been a lot of progress on that, looking at it at different scales. Now, could we do it globally? We have never paid for the research to scale it up. There's a very interesting new book that came out by a woman, Holly Buck, who's at UCLA. She has spoken here, and it's something I think we have to invest in. If you look at the consequences of this, of sea level rise of 8, 10 meters, seems to me one has to do the research. Anybody? Giuliano, don't agree with your former mentor. It'd be better if you agreed with me.
No, I'm kind of with Gary on this one. I just want to add that even if we could mimic a big eruption, we would kind of make less sun radiation would get into the Earth, but one big unintended consequence of that is acid rain. So I'm not too excited about that one.
And I agree. I don't think SRM is the answer, but yes. Okay, right over here. Ron Salk. Do we have a microphone over here? Oh, wait, we got one in the back, then we'll get you next. Ron, go ahead.
Jerry, you just said 8 to 10 meters, and the highest number that was shown by Gary was something like, what, 89 inches or something like that in the 1 in 200 case? 89 inches is what, maybe 3 meters?
No, Gary, characterize the potential range of sea level rise that you talked about. And certainly, if all of Antarctica were to melt and Greenland were to melt, which they have in the geologic past, then we're talking about 250 feet or so, 225 feet. Is that going to happen in the next century or two, or even in the next 1,000 years? No. But within the next century, what did you have as the possible range of sea level rise?
By 2100, I think we're in the range of 3 feet has been what we've been using for a long time, and Jerry said IPCC this last couple of weeks said, well, maybe more like 2 meters, and the extreme has been 10 feet. And I think what's important is we need to keep monitoring and measuring and updating, because a lot of places we don't even have tide gauges, so we're using a global number when in fact locally it may be very different than that. So
Sure.
It's going to be a constantly changing landscape that we need to keep monitoring before. I think we don't want to cut off future options, so I think we need to proceed sort of cautiously.
We have two right down here.
Sure. I know you'd be disappointed if I didn't say this, but you opened the door when you mentioned Holly Buck. And we have booked her, you and I, for our January 19th symposium here by the League of Women Voters and the Aquarium of the Pacific, right on the heels of her book coming out.
Thank you, Ron. One right down here.
We historically had inland seas.
Yes.
For the short term, instead of moving our cities that we will gradually have to do, is there any feasibility to, again, creating inland seas in our land that's not arable?
Who would like to do that? Gary, that's a geology question. You're the oldest one up here. You've probably seen this.
He's shooting the messenger. Well, that one image that showed if we melted all the ice, the whole Central Valley becomes an inland sea again. And in fact, the Central Valley became an inland sea in 1861 with the greatest flooding California has ever experienced. We had a sea that was 30 miles wide and 30 feet deep for months. I guess in a place like California, where so much of the low-lying land is so intensively used for agriculture and development, I think entertaining the idea, it's like, I would say we're never going to build another big dam in California. No matter how much water we need, there's just too many people involved and too many environmental issues. So I'm not quite sure what the objective would be to create an inland sea. Is it like making more coastline that people could live along, or? Oh.
There you go. There we go. No.
You know, I think we have to look at volumes. There was a Republican congressman a little while, I shouldn't say Republican, he was a congressman from Alabama that said sea level's rising because those rocks are falling off the cliff into the water. So I think we have to keep scale in mind. And that's a good question. It's not a complicated thing to say, well, to keep sea level what it is at today, if we know how many square miles of ocean surface there is, how big of an area would we need? And how deep could we fill it? But I think Nevada's a great idea.
So I want to ask Alyssa a question. One of the things the Nature Conservancy really feels strongly about is if communities are going to wrestle successfully with this issue, they're going to have to be able to have dialogues, conversations where they have rational discussions of what the facts are, and say a word about that. This is a pretty rational group so far tonight.
Yeah, I mean, I think one of the things that that we're really interested in, obviously, with the Nature Conservancy, we've been looking at nature-based solutions across the country and really across the world. And one of the things that we've come across is to be able to put in place some of these nature-based solutions, which really do have carbon sequestration benefits too. I mean, these places. Some of these places we're talking about used to be estuarine systems, and now we've obviously filled and changed these systems drastically. That we need to be able to have the space for some of these solutions, both for the benefit of absorbing a lot of the carbon that we're putting into our atmosphere, but also to protect communities. We saw across the East Coast after Sandy, places that had dunes, marshes, the communities behind them fared a lot better. And so, one of the things that we want to make sure that's happening in California is that we're not closing our options to be able to employ some of those down the road. This isn't something we're going to do tomorrow in a place like here or other places along the California coastline. But for us to have these really meaningful discussions about what is the future of this place and what's the vision that the community has, and being able to have meaningful conversations about how we might get there in the next 50 to 100 years.
And we in California have destroyed 97% of our wetlands, and on an aerial basis, wetlands and mangroves are more effective at removing CO2 than rainforests. Who has the next one?
Do you still own the property that you live on if the building is flooded and underwater? In other words, we own 300 feet up in the air for airspace. How far down do we own for property rights? I lost 30 by 80 on Naples Island. We could be flooded and be underwater. Can we bring back a houseboat like Tiburon?
Who can address that?
Cheryl Mann.
How far down does a property owner own?
That's a really interesting question. Pardon?
Do you know, Alyssa, the answer to that?
I'm not a legal expert on coastal management, but I do know that a lot of these questions are going to ultimately be tested in the courts. California, the coast is, we have the Coastal Act, which protects essentially the beach for the public, and that's an ambulatory line. And I think that will certainly, as sea levels rise and this issue becomes even more prevalent, it's certainly something that's going to be tested in the courts. So I don't have a answer for you on that. I don't know, Gary, if you have some thoughts about that.
I'd just add two things. One, the state owns everything below mean high tide. So as sea level continues to rise, mean high tide's going to rise, which means the state will own it. There's also an awful lot of property in California when it was originally divided or sold that the owner kept mineral rights
Yeah, the moat rights. We don't
below
have
the surface.
We don't have the moat rights in Long Beach.
Okay.
Okay.
Well, we'll have to do some research. Question down front here. Right here.
Thank you. I wanted to ask the people from France, does the French coastline have wetlands? And if so, who maintains them?
Yes, we have in our coast. There are many wetlands because we have the coast is we have the Lido, then wetlands, and then inland, and so it's a big part. And as in USA, they are threatened, and we have lost a lot. But nowadays we are preserving them. We have zoning to protect this area. We have also the Conservatory of Coast, which is an institution which can buy areas of wetlands. But we think it's less used in France to promote fight against sea level. We protect them, but in California we often see in public documents that restoration of wetlands is also something for fighting sea level rise. In France, the discourse on sea level rise is present, but is how can I say? It's without too much figures. It's not so precise as in California, where public or scientists shows many figures to objective the sea level rise. In France, we'll say sea level rise is arriving, but is not so used. We have not, for instance, your web tools where people can go and see the level of the sea level rise. So that's quite different, I think.
Just to, wetlands are not considered as important in terms of sea level rise in France, but mostly in terms of biodiversity, with specific zonings around biodiversity.
And we heard this morning at a forum at the Beckman Center that more of the sea level rise mediating it through wetlands is more prominent around San Francisco Bay than it is in Southern California, although there are a few examples down here. That's that special territorial recomposition. I love that.
They're political
only the French
scientists.
would come up with that.
They're political scientists.
All right, who has the next?
I have a microphone here. So I wonder if French government and industry is collaborating with the Dutch, because it seems like the Netherlands are in maybe a more immediate situation or a faster paced situation, based on the news, and it seems like they're doing a lot of nature-based stuff plus a lot of high technology things. I'm just wondering. You mentioned a lot of collaboration with California. I'm just wondering if you're working with the Dutch as well.
Many elements on that, except that Dutchland are pointed as the good pupil in Europe because all their land are beneath the sea and they manage to protect themselves. But it's a model of hard armored protection, and at least in France, we now most promote ecological engineering, dune restoration, and the Dutch don't do that a lot.
I can speak a little bit to this. We've brought some of Dutch colleagues to California, specifically to Los Angeles, actually. Phyllis Gerfman from USDC Grant. We collaborated on a study with them. I would say that they, similar to how you guys presented, spent a lot of time fighting against the sea, and now are starting to readjust to figure out how do they accommodate and live with water. And obviously they've been dealing with flooding for a very long time and have a lot of experience. And so we brought them to look at the Los Angeles coastline and bring some of their lessons to that. So.
And they were very involved in the San Francisco Bay study, Resilience by Design. So, yep. All right, we get a microphone.
Here, I have a question.
Right here. This one isn't about the coastline, but I didn't expect to learn as much as I did about climate change, in the broader. And you've spoken about adaptation and sequestration and so on. I've heard very positive things about regenerative agriculture and the ability to pull down carbon and put it back in the ground if we change the way we do agriculture. Anyone know about that?
Yes, and it's very promising in the central part of the country, in the Corn Belt, in places like, well, even on the East Coast in Pennsylvania, the drainage basin of the Susquehanna River that causes problems in Chesapeake Bay. Regenerative agriculture and also replanting lots of forests where we had forests and stopping deforestation. Those are soft approaches to geoengineering. We've got one hit. Adina, we've had a hand up down here.
We talk about a lot of things going to happen. What are the resources to counteract the problems? Where's the money going to come from with all the things we're talking about? And in our case, would tidelands be a beneficial source for us?
Somebody like to answer that? Well, how are we going to pay? The problem with tidelands is the oil will run out in 10 to 15 years, and those of us who live in Long Beach, that's one of the largest sources for the budget of Long Beach, and that will disappear.
Yeah, I mean, I would say that there's a whole body of research right now about innovative financing and funding for this problem. Obviously, for a little while now, we're mostly in the adaptation sphere, really dependent on big bond measures that the state will pass. And I think that will certainly be part of the mix for a while, but I think we do need to think a little bit more creatively. There's a whole body of work looking at insurance products and how do you tap into kind of the private funding world for some of these issues, because I'm not sure we can, and whether or not we'll have the political will, I hope we will, to continue to do some of this public financing, but it's a big challenge.
Another interesting example, kind of an analog to Long Beach, where there is a peninsula and there are 2 rows of houses. And the proposal was for the city to buy the row of houses closest to the ocean, rent them out, and take that money and put it into a fund to help fund protection. Because you've got probably 20, 25 years of good rent of very attractive homes. Yes, go ahead.
Yeah, that ties right into my question. It's more local, short term. We're here talking about the peninsula, Belmont Shores, and Naples. Do you have any information regarding short-term engineering mitigation for these areas? Because right now we do have seawalls that are high enough to keep the seawater out, but we have tides that are higher than our sidewalks.
Who wants to address that? Gary, make a case for toe jetties or short groins.
As soon as you mention engineering, it conjures up armor. And I think, which is armor. I mean, I'll say armor is seawalls, revetments, the 2 big categories. There's clearly private property benefits to coastal protection. You're protecting your home. There are negative public impacts of coastal protection, which is one reason why the Coastal Commission has decided we're not going to do this anymore. And there's a whole range of those, from building a structure on the beach that takes up beach area, to loss of sand if they're up against a cliff or a bluff that's eroding, no longer add sand to the beach, to one of the biggest impacts that we'll see in the future, and the USGS did a big study of this for Santa Monica Bay in Southern California, that if there's no protective structure and sea level keeps rising, I mean, we had a beach 10 miles offshore 18,000 years ago. Sea level was lower. And as sea level rose, the shoreline moved inland, we had a beach. We still maintain the beach. But once we put a wall in and we continue to raise sea level, we're going to drown or flood that beach. So that's one of the biggest impacts. We lose the public beach while we're protecting infrastructure, private property. And I think that's one of the reasons why the Coastal Commission is saying the negative impacts to the public as a whole for beach use and recreation are the things they worry about. Quite frankly, the Coastal Commission does not care about private homes. I mean, it's sad to hear, but that's not their priority. It's public benefits and resources and access. So there certainly are those objectives or those options out there. My own sense, and I don't work for the Coastal Commission. In fact, I work with property owners trying to deal with the Coastal Commission, is they're getting firmer and firmer on no more armor. And I think if you think about nourishment, which is another option, it's very expensive until you start putting barriers in. That sand's not going to stay there for very long. So there's no... I have a close coastal engineering friend from Berkeley, been there for many, many years, and every time I'd come up with some great solution, he'd say, Gary, for every complex problem, there's always a simple answer, and it's always wrong.
But Gary, you showed those photographs of a series of short groins that can keep sand.
That is one, yeah.
That's a different engineering approach.
Right. And that's one thing we just submitted a paper on, saying let's relook at groins, because that's a way to keep sand in place without impact. You're actually widening the beach rather than making it narrow. And I was under the impression for many years that the Coastal Commission was against groins. In fact, when I finally talked to the coastal engineer, he said, well, no, we're not really against groins. We look at them like anything else. So we're proposing we start looking at groins again, basically as artificial headlands that are going to widen beaches. It could last a long time.
And I think the peninsula should be looked at from that perspective.
Just want to add a couple of things real quick. I don't know if Gary remembers, about 2 years ago, we were at the UCI event, just like the one today, and there was a person from the Dutch government that was there. And he said, I'm going to tell you the secret why we're so good at managing against and protecting against sea levels, and it was taxes. So he basically said they tax a lot of people and a lot of things, and a lot of those taxes go to coastal protection and management. So and the other comment, real quick, we did a study in Imperial Beach about 2 or 3 years ago, looking at the sea level rise vulnerability assessment, and the option that you mentioned, where the city would acquire like the beachfront properties and rent them out at a premium as vacation rentals. So the numbers, the economists ran the numbers, and they showed that the city would recover their investment within like a mortgage lifetime of the property.
Lots of options. We have time for a couple more. Who's got a microphone?
I want to thank you for your presentation. It was more than enlightening. Regarding the land nourishment, I found that kind of intriguing. How do you decide what area to put land nourishment in, and what does it entail, and what's its longevity? And do you think that that also would work in California, and what kind of soil do you have to have? Thank you.
Are you asking specifically about sand?
Yeah,
nourishment?
about the sand nourishment. What is all that? I wanted to get a better understanding of that, and if also where it showed it being done in France, if it could also be done in California, what's needed to be able to do that?
Maybe Gary will have a thought about this, but I'll take a first stab at that. I think one of our biggest problems, say for the example of the Dutch, they have a lot of sand to work with to do these sort of big nourishment projects. Here in California, we don't have access to huge sand sources. Obviously, we've blocked a lot of that sediment coming down from our rivers by channelizing and damming up our river system. So that means that the natural way that would feed our beaches would come through the watershed. And we're not getting nearly what, if you look at the historic conditions, not getting nearly what we would need. A lot of Southern California, we have these kind of big, iconic Baywatch beaches, right? Those are pretty artificial beaches. We had some huge dredging operations that happen at different phases, like putting in the ports of LA and Long Beach harbors, and place that sand there. We aren't doing those types of operations now, and certainly don't have access to the kind of, and you probably have some more specific thoughts about sand availability.
So the East Coast has lived on beach nourishment. They've spent over $5 billion, New Jersey, New York, Florida, taking it from offshore where there's a lot of sand. California is different, other than the projects in San Diego, a little bit along this coast where we sort of back past some sand. We generally haven't done that. And as Lisa pointed out, in Southern California, about half of all the sand that used to come down the rivers is now trapped behind dams and debris basins. So our beaches have, interestingly, it hasn't been a sort of one-to-one loss. We haven't seen necessarily beaches narrow because of all those dams, but beaches that were always narrow, and if you look at northern San Diego County, Encinitas, Leucadia, Solana Beach, those vertical cliffs never had wide beaches in front of them. But they've nourished them, and the sand kept moving right on through. This area is different because it's still sort of part of this nice, broad, sweeping bay. But we can have a big El Nino or a big storm and lose that very quickly. So where do we get the sand? Most of the sand that moves offshore, moved offshore because it was too fine grained to stay on the beach. So putting that on the beach, it's not going to stay there. Some people propose building cobble beaches and gravel beaches. They'll stay there, but they're not real comfortable. So, and again, because it's so short term, unless we put in groins, which I think is a much better idea to stabilize what we do have, realizing that there are some considerations when you put those in affecting downcoast beaches, I think is one thing. We lose about 1.2 million cubic yards a year of sand down our submarine canyons. So we've got those all along the California coast: Magoo, Hueneme, Doom, Redondo, Newport, La Jolla, Scripps. It's lost forever. It's going down to 12 or 15,000 feet. So stop that before it gets there. And there's a lot of different kinds of groins. We can build geotextile groins. We can build rock groins. We can build concrete. We can build timber. We can make them longer. We can do some pilot projects. But that would be a huge change in what we've done for the past without having to suck sand off the seafloor or take it out of the mountains. And if you followed Broad Beach, which gets much more publicity than it should because all the movie people live there, their beach is gone. They have their septic tanks on the beach, which is a problem. Even if you're a movie star, it's a problem. They're trying to get 600,000 cubic yards of sand from these sand quarries up in Ventura County, like 60,000 dump truck loads, and Ventura County saying, we don't want you driving 6,000 dump truck loads or 60,000 dump truck loads across our highway. So that's still being, even though that was a proposal, let's nourish Broad Beach, and then when it goes down the other end, we'll back pass it and we'll bring tractors and move it back. We've got to find something better than that.
I think we heard a great solution here if we dig a very large canal into Nevada, then excavate Nevada. We'd have all that sand, and we could get rid of a lot of the ocean, keep sea level. I think that's a winner. We're going to have the Art Center college. Yeah.
I was going to say one more thing. I mean, obviously, we've mostly been talking tonight about vulnerability to our built environment, right? The things that we've put and built in along our coast, but also at risk are our natural areas. The Nature Conservancy published a study last year that looked at the vulnerability of all of our coastal habitats, from beaches, intertidal habitat, marshes, freshwater wetlands, And we're, when you look across the California coast, we could lose as much as 59% of all of our coastal habitats. When you look at beaches, that could be as high as 70%, like especially down here in Southern California. And you know, I think I think all of us that live here in California, our California coast is kind of what makes this place so iconic and amazing, and all of the species and kind of habitats that we have here, and we also could lose those as well as the places that we've built to enjoy them.
So we may change our attitude on how to protect the coast. We're going to take one more. Who's one more? We're going to have lots more of these. I think.
This is a question for Gary, and this was your slide with showing the 300 million years of sea level rise, and there were several spikes in it where it went up and then it went down. Why did it go down? I mean, why were there the spikes?
So it was actually 350,000 years.
Okay.
But it's okay. It's like the Earth is going to end in 5 million or billion. It doesn't matter. So the forcing for those are these astronomical cycles of the wobble and the tilt and the eccentricity. And those happen over, again, 100,000 years, 46,000 or 42,000. So when those cycles produce a cooling period, a couple things begin to happen. But essentially, we start to sequester more seawater. On the continents is ice. And seawater, as it gets cooler, contracts. So we lower sea level roughly 400 feet. So that's the downturn. And then when those cycles return to a warmer period, ice starts to melt, seawater expands. And there's some feedback loops in there, which when it starts to get warmer, the ocean will give off more CO2 that exaggerates the warming. When it starts to get warmer, what's happening today is the ice in the Arctic, which isn't a continent, but it's floating ice. As ice, it reflects a large amount of sunlight, but when it turns to water, it absorbs more sunlight and it gets warmer. The other thing we're just starting to understand is permafrost, which has huge amounts of methane. And as the permafrost is starting to thaw, it's releasing methane. So that's another feedback that sort of accentuates those normal astronomical cycles. So those are pretty predictable, not the little details, but right now all those cycles should tell us we're going into a cool period, but we've overridden that with greenhouse gas emissions.
Well, I thank all of you for your thoughtful attention this evening. If you have ideas of people you want to hear from, just send us a note. Topics you want discussed, send us a note. And so please join me in thanking our outstanding panel. Thank you.
Thank you so much. Thank you. That was a gentle crowd.
Thank you, Laura. Sylvain, thank you.